This is the completed reading for the rest of Chapter 2, Lesson 1, Properties of Minerals. We'll read page 56 through 61. Crystal structure. The atoms that make up a mineral line up in a regular pattern. The pattern repeats over and over. The repeating pattern of a mineral's atoms form a mineral's crystal structure. All the crystals of a mineral have the same crystal structure. Scientists can use crystal structure to identify very small mineral samples. For example, scientists can bounce a powerful beam of particles off very small crystals. Because the atoms that make up minerals line up in regular patterns, these beams produce distinctive patterns of light. Very cool. As shown in figure 7 up here, this is halite. It's a cube, and so the direction goes along to make it look like a cube. And then in here, it is a 1, 2, 3, 4, 5, 6, so a hexagonal shape and a hexagonal prism like we learned in math. So it'll bounce off all the sides, and they know that that is a six-sided shape. Very cool, huh? So different minerals have crystals that shape differently. Halite crystals are cubic, and they are shaped like a cube. You can break a large piece of halite into smaller pieces, but the smaller pieces still contain crystals that are perfect cubes. Pretty cool, huh? Geologists classify crystals by the number of faces or sides on the crystal. We're doing this in geometry for math. They also measure the angles at which the faces meet. Very cool. Page 57. Cleavage and fracture. I was telling you about talc on the last lesson, and it comes off in little sheets just like that. You can just peel it right off like a piece of paper. It's pretty cool. Cleavage, you may be familiar with how the mineral mica can split apart to form flat sheets. A mineral that splits easily along flat surfaces has a property called cleavage. So if it peels apart easily, it's called cleavage. Whether a mineral has cleavage depends on how the atoms in the crystal are arranged. The way atoms are arranged in mica allows it to split easily in one direction, and it's shown in this picture. Most minerals do not split apart easily. Instead, they have a characteristic type of fracture. Fracture describes how a mineral looks when it breaks apart in an irregular way. Once again, let's talk about Oreos. Oreos peel apart in layers, don't they? But if you try to peel apart a chocolate Chips Ahoy cookie, it's just going to break into pieces. So Oreos have cleavage and Chips Ahoys have fractures. Fracture describes how a mineral looks when it breaks apart in an irregular way. For example, when quartz breaks, it produces curved shell-like surfaces. Special properties. Some minerals can be identified by special physical properties. Calcite bends light to produce double images, as shown in this figure 9. Double images, so it made it look very cool like that. It's shown other minerals conduct electricity. Metals conduct electricity, and they glow when placed under ultraviolet lights or are magnetic. So very cool. They have different properties, and that's kind of how they tell them apart. And then page 58, we will talk about how do minerals form. On a rock collecting field trip, you find an egg-shaped rock about the size of a football. That's pretty big. Later, at a geological lab, you split the rock open. The rock is hollow. Its inside surface sparkles with large amethyst crystals. My favorite. Amethyst is a type of quartz. You have found a geode. As shown in figure 10, a geode is a rounded hollow rock that is often lined with mineral crystals. Geologists believe that crystals probably form inside a geode when water containing dissolved minerals seep into a crack or hollow in a rock. Slowly, crystallization occurs. Sorry, I lost my place. Minerals. Scientists or geologists believe that crystals probably formed inside the geode. Slowly, crystallization occurs, lining the inside with large crystals that are often perfectly formed. Crystallization is a process by which atoms are arranged to form a material that has crystal structure. In general, so this is the key fact, minerals can form in 3 ways. Some minerals form from organic processes. Other minerals can crystallize from materials dissolved in solutions. And finally, many minerals crystallize as magma and lava cool. This is most often it's magma that cools. We'll talk about later on, unless it's in this chapter, if it cools quickly, it won't have crystals. If it cools slowly, it will have crystals. I know there's little mineral kits that you can buy at the store, make minerals, grow them. If you put salt in water and then you boil it, you'll be left with the crystals of salt on the bottom. So those are some cool experiments. You can watch experiments online too about how crystals form. All minerals can form by inorganic processes. However, some minerals can only form by organic processes. For instance, ocean animals such as clams, corals, they produce shells and skeletons made out of the mineral calcite. So they have their bones or their shells, and they sit at the bottom of the ocean, don't they? Minerals from solutions on page 59. Sometimes the elements and compounds that form minerals can be dissolved in water to form solutions. A solution is a mixture in which one substance is dissolved in another, like salt water or sugar water. When elements and compounds that are dissolved in water leave a solution, crystallization occurs. Minerals can form in this way in bodies of water on Earth's surface. So crystals form just on Earth's surface as it would in their little bowl or pan of boiling water with salt. But the huge selenite crystals shown in figure 11 formed from a solution of hot water that cooled underground. Minerals can form by evaporation, and they can form from hot water solutions. So Giemsen rose and silver. Some minerals form, the solutions evaporate. Salt water, we talked about that. In a similar way, deposits of mineral halite formed over millions of years when ancient seas slowly evaporated. Such halite deposits are found in America's southwest and along the Gulf Coast. Gypsum and calcite can also form by evaporation. Sometimes gypsum forms in the shape of a rose. Pretty cool. Deep underground, magma can heat water to high temperatures. The hot water can dissolve the elements and compounds that form minerals. When the hot water solution begins to cool, the elements and compounds leave the solution and crystallize as minerals. For example, quartz can be crystallized from out of a hot water solution. Pure silver is also often deposited from a hot water solution. Gold, too, can be deposited in this way. Pure metals that crystallize from hot water solutions underground often form veins. A vein is a narrow channel of slab of mineral that is different from the surrounding rock. So it'll be veined right throughout it. It's not just one big chunk. So it kind of worked its way through. Page 60. Minerals from magma and lava. Many minerals form from magma and lava. Minerals, key fact, form as hot magma cools inside the crust or as lava hardens on the surface. When these liquids cool to a solid state, they form a crystal. The size of the crystal depends on several factors: the rate at which the magma cools and the amount of gas the magma contains, and the chemical composition of the magma all affect the crystal size. Magma and lava are often rich in oxygen and silicon. Minerals that contain these elements are called silicates. Together, silicates make up a majority of Earth's crust. Minerals from magma, oh my gosh, that is so cool. There's all kinds of different ones. Magma that remains deep below the surface cools slowly over thousands of years. Slow cooling leads to the formation of large crystals. Quartz, feldspar, tourmaline, and mica are common silicate minerals that form from magma. However, minerals from lava. If magma erupts to the surface and becomes lava, the lava will cool quickly. There will be no time for large crystals to form. So this looks like a honkin' rock. This looks like beautiful jewelry, right? Instead, small crystals form. Lucite and olivine are silly minerals that can form in lava. So if it's underground, it's slowly cooling, making very cool rocks and minerals. This one is on top, it cooled fast. In this picture, it's showing you that there's cool magma lava under here. We have the veins right here that is saying that it kind of spreads throughout. Minerals formed in hot water solution, minerals formed in lava cool, and then minerals formed by evaporation on the coastline here. So you can continue looking at that picture if you would like. Very last page of the chapter is 61, where mineral resources are found. Very cool map there. Let's find Michigan. We're over here. Nothing by us. Earth's crust is made up mostly of the common rock-forming minerals, combined in various types of rock. Less common minerals are not found evenly throughout the crust. Instead, several processes can concentrate these minerals or bring them together in deposits. An ore is a deposit of valuable mineral contained in rocks. Iron ore may contain the iron-bearing mineral pyrite, magnetite, and hematite. Lead ores may contain galena. These ores are mined and the iron or lead is separated from the rock. Graphite and sulfur are sometimes also mined. Figure 13 shows major mining areas. I'm going to share with you real quick because in one of our next chapters we talk about the plates underneath the continents, the tectonic plates that are under there, and there is two plates that join together right here. We can't see them because they're underneath the continents, but where this meets, there's a crack, and that's where the magma and the lava comes out from under here. There's also another plate that comes around here where it meets, and where those two plates meet, that magma and that lava can come up in between those two tectonic plates. That is the end of our chapter. Please use your book tomorrow to answer the questions on the quiz. You may also replay the videos. Hope you enjoyed the reading.